find there are a lot of mathematical equations. So in the slide from Glasgow, you will find there are a lot of mathematical equations. And the lecture in Glasgow from the aerospace science. So that's why you will find the word of aerospace in the slides. But the lecture is open to the aerospace students, to the ST students, to other students in Glasgow. So we are covering the same material. And also in the Moodle, you will find another set of slides that I'm developing. So I will rely more on the slides here. But basically, we are covering exactly the same material. So if you compare these two sets of materials, you will find they are exactly the same. And I will try to put more words on the slides to help you to understand the review of the lecture. And also, I will encourage you to take the handwriting notes during the lectures. So because there will be a lot of mathematical derivation. So to learn the mathematics, the best way is to do it by yourself. So there are no shortcuts. So I will encourage you to take the notes. And then later I will also scan the handwriting notes and put on Moodle. You cannot take every details. So that will help you to review the lectures. So in the last lecture, we start this course. So we know this course mainly on the path planning problem. So for autonomous vehicles, important problem is the guidance. The guidance from the starting point to the destination is the path planning problem. So the problem formulation is something like this. So we have a starting point and we got a destination in a 2D space. If there are no obstacles, then the path will be quite straightforward. It's just the shortest line will directly connect the starting point to the destination. There will be one of the best paths because it's the shortest. But however, if there are some obstacles, your vehicle will require to avoid these obstacles and find its way. So there will become more complicated. So we discussed in the last lecture. We mentioned that there are two sets of methods. So the first set of methods is a continuous path planning problem. The other one is discrete, digitalized problem. In the last lecture, we introduced the continuous path planning problem. So basically, essentially, the problem is trying to optimize cost function. So how to design this cost function is up to the designer of the problem. So you may design this cost function to reflect, for example, the traveling time from the starting point to the destination. Then you optimize this problem, you will get a time optimal solution. So if you design this cost function to describe the traveling distance from the starting point to the destination, when you optimize this problem, you will get the shortest path problem, the shortest path solution. So this cost function is optimized subject to the dynamics of your vehicle. So in the path planning problem, we try to simplify or try to minimize the dynamics. So it's not a real dynamic of your system. but you consider the vehicle just a point object. So we can consider the locations, the velocity, and also the acceleration. The acceleration can be linked to the force applied to the vehicle. Force, the acceleration is equal to the force divided by the mass from your dynamics. So it's also subject to the initial conditions, the initial location, initial velocity, and initial time, and also the final conditions of the problem. So your estimation, your final velocity. And sometimes, also usually, your acceleration is subject to a boundary. So you cannot take any values. It must be within a boundary, but a lower bound and upper bound, lower bound and upper bound from the x direction and y direction. So from this problem definition, we are actually dealing with the differential equation, and this set of differential equation are second order. They will be second order differential equations, and we also want to optimize the equation. So essentially, this problem is an nonlinear programming problem. So it's actually quite difficult to solve. So in order to solve the problem and to save the computation, one of the methods is to discretize the problem. So it's similar to the idea that we used in the ESP4. So we try to sample the problem and try to discretize the problem. But certainly the methods will be very different. So for the discrete path planning problem, the main advantage will be it will become more computation efficient. So you can save a lot of computations, and the computer is readily used to solve this problem. So the second category of the techniques will be discrete path planning. So the basic idea is to discretize the differential equation. So from the definition of the derivative, so in the differential equation, so from the continuous path planning problem, so we have this set of differential equations. We have this set of differential equations. So the first one is x dot equal to Vx. So I just copied it down at here to see how can we discretize this function. So for the continuous problem, we have this differential equation that x dot equal to Vx. So we have another three equations: the y dot equal to Vy, the Vy dot equal to Vx, and the Vy dot equal to Vy. But I just use this equation as an example. So based on the definition of this derivative, we know the x dot. So the meaning of the x dot is the derivative in terms of time. So it's equal to dxt dt. So it's not a derivative in terms of x, but it's a derivative in terms of the time. So the definition, from the definition of this derivative, it's a limitation for the x because it's in terms of time. So we take t plus delta t minus xt divided t plus delta t minus t. So we got delta t. And for delta t, it's approach to 0. So this is the definition for the derivative, and this one is equal to Vx. So if we want to remove this delta t, delta t, then it's not exactly equal, but will become an approximation. So if we remove this delta t, it becomes xt plus delta t minus xt divided by delta t is approximately equal to Vx. It's the time of t, Vx of t. And now the delta t is become a design parameter. So you can choose the delta t by yourself based on the desired accuracy and the computation cost. So we multiply the delta t from two sides. We have this xt plus delta t minus xt equal to Vxt delta t. So this can be also rearranged to this form: xt plus delta t equal to xt plus Vxt delta t. So currently it's still a continuous timing because we are using t. So in the discrete format, we want to replace the t by an index. So it's similar to the concept in the ESD4. So now we're using the notation that this t we replace by tk. Tk, I will say, replaced by k. It's become an index. So this t plus delta t will become tk plus 1. So it can be also simplified to k plus 1. So we ignore the delta t in this equation. So if we introduce the index of k, then the equation becomes xk plus 1 equal to xk plus Vxk multiplied by delta t. So now this equation becomes discretized equation. So similarly, we need to discretize the other three equations. So the other three equations can be discretized to yk plus 1 equal to yk plus vyk delta t. So this one from the equation of y dot equal to vy. So we can also discretize this function to this form. So similarly, we have the v xk plus 1 equal to vxk plus a xk delta t, and this vy k plus 1 equal to v yk plus ayk delta t. So the method will be exactly the same as before to discretize this set of functions. So now the function become discretized. The dynamic function become discretized. So in our continuous planning problem, we also got this cost function. So similarly, you can discretize this cost function. For the initial condition and for the final condition, it's already in the correct form. So for the acceleration, we got this range. We got a range, a lower boundary and upper boundary for the acceleration. So in the discrete problem, we can further discretize the acceleration. So for example, assume the acceleration inputs are confined to a finite side. So assume the accelerations are confined to a finite side. So assume the possible, for example, the possible AX can only take 4 values, for example, -5, 0, 5, 10. And the AY can only take 3 values. So now the problem become completely discretized. So there are 12 combinations. So there are 4 options. There are 3 options. So you know totally there are 12 options. 12 options. So for example, if your vehicle is in this location, your xy, and if you apply all these potential accelerations, there will be 12 potential positions in the next step. So assume this is the position for index of k. So for the k plus 1, there could be 12 potential positions. So for example, if you apply the force, the Stephen force, there could be totally 12 potential positions. Because there are only 12 potential input, so each input may make a different position. So there could be totally 12 combinations. Combinations. So now we consider the problem in our path planning space. So from the starting point, you apply these 12 possible forces or 12 possible accelerations. There will be 12 point or 12 potential positions. And for each potential position, we apply the 12 combination of force. We will generate another 12 potential points. So eventually this will become a tree, a big graph of tree. So if your algorithm potential is well defined, so hopefully one of the final point will be equal to your final destination. So it depends on your design, our truth of the acceleration. So if the acceleration are well defined, then in this big tree, one of the nodes will be falling on your final destination and avoid all these obstacles. So that path will be your designed path. So this is the idea of the discrete, one of the methods for discrete path planning based on the graph theory. So another technique to solve this discrete path planning problem is similar to our continuous path planning problem. So you also solve this optimization problem, but subject to this discrete set of equations. So it will become an optimization problem. So essentially for the discrete path planning problem, we will discuss two techniques to solve the problem. The first technique is based on the optimization to solve all these equations by using the optimization methods. So the second set of techniques we are going to discuss is to use the graph theory. So you build up this kind of graph. Eventually we'll find potential paths. For example, with the shortest distance from the starting point to the destination. Okay, so this introduction of the course. So next we will discuss the first method, this potential function guidance method. So this method is actually quite simple. It's quite straightforward, but it's very robust and still widely used. So for this potential function method, the concept is not new. Actually, you already know the concept very well from your previous studies, especially from your course of dynamics. But maybe you have been using or addressing the concept from different way. So I think you already know the concept of the potential functions. So there are many ways of the potential function, I'll say the potential energy. So for example, if you look at the fluid flow around obstacles, I'll say the gravitational force. So it's a kind of potential function. So in the potential function, we have a concept of the potential energy, and the potential energy are actually linked to the conservative force. So this force in our path planning problem, you know the force can be linked to the acceleration. So this is why we can use this method to solve this problem. So the basic idea of the method is to define artificial potential energy function. In the past planning problem, we don't have the potential energy, the concept of potential energy, but we can artificially define a potential energy. So we can define this potential field function of U. So the U will be a function in terms of your location, your vehicle location X and Y. So from this potential function of U, we can derive the force, the conservative force. So the conservative force is given by this famous equation. So it's a derivative of U in terms of your variables. So in this case, in the 2D space, we have X and Y. In the 1D space, so for example, in the gravitational force, it's just H, the head of your object. So once we have an equation for the force, we can link the force to the acceleration from the Newton's second law. So we can link this by using the mass of your object to the acceleration. And now you can recall the equation that we developed in the continuous path planning problem. So if we know this acceleration, so the acceleration, if you integrate it once, you got the velocity. If you integrate the acceleration twice, you got the location. Okay, and so the location will be this path, will be this potential path from the starting point to the destination. So these are the basic idea of the method. So for the potential function method. So the concept is actually very simple. So assume you got so for example, if you got a sink, and here is the lowest point. The lowest point is the lowest point. So if you got, for example, a drop of water, so this water in theory will automatically find its way to the lowest point. So although there's no intelligence in this drop of water, but this water can automatically find its way to this point, to the destination. And so it is the simplest scenario. And if there is an obstacle on the way, then the drop of water will be able to avoid this obstacle, for example, by this method, by this path. And also eventually it will come to the destination. So this is the idea. This is the idea of this method. The idea behind this method. So even for a water drop, with no any intelligence, eventually it can find its way to the destination. So this potential function method is trying to simulate this idea, or try to simulate this physical phenomenon. So example A good example of this is the gravitational force. So we know this potential function are somewhat linked to the conservative force. So in the case of gravitational force, assume we got an object with H, with height of H. So this is the ground surface. So we have an object with a mass of m at the height of H. In this case, we know we can define this potential energy. This U can be defined by mjh. So this function, if we consider the mass to be a constant, and the j is a constant, so it becomes a function of h. So this is the potential energy. And from this potential energy, we can develop this conservative force. This force equal to is a minus. So from your dynamics, you know this equal to minus du dh. Minus du dh. So it's a minus b u dh. So this is just equal to minus mg. So this is the basic idea behind the gravitational force. So in our so this one is just a simple introductory example. So in our method, in our path planning problem, we need to define a potential energy function. But actually, you can define this function in any way to try to simulate this equation. So we know this function is just an artificial function. So this function should be a function of the location, should be in terms of x and y. So you can define this function. So actually, there are many ways to define this function. But so for example, we can define this function in this way. This becomes is equal to x squared plus y squared. So for the physical, so why we want to define in this way is because you know in the 2D space, x, y, so we have this origin. So if you got a point, x and y, so the distance, this distance is given by, this distance given by a square root, x squared plus y squared, the square root of x squared plus y squared. So actually, if we define the function in this way, we try to simulate this h in the 1D space. In the 1D space, the h defines the distance between your object to the ground. And in the 2D space, we define the function to reflect the distance from the point to your origin, or to say the destination. So if we define the function this way, we can define the force. So the Fx equal to minus du dx. So this equal to minus, so the y is constant, so it's minus 2x. So similarly, we can define this Fy equal to minus du dy, so it's minus 2y. So the force, we know the force can link to the acceleration, so the Ax is going to be linked to equal to Fay. So from here, we can get the equation for Ax and Ay. From this, we got the equation for Ax and Ay. So if you calculate the equation, we got the Ax and Ay. If you further integrate this, you got X and Y. So you got the path. So if we define the potential function in this way, we know the destination is at the origin, is at 0. So if we are trying to calculate the distance between the object and the origin, so we are trying to get the vehicle to the point of 0, 0. So what about to a standard destination? So for example, if we have this starting point, it's the starting point, and we got this destination. So the coordinate of the destination is xa and ya. So xa and y will generate attractive force. So it will generate something like this. So this is the first force, I'll say the first potential. So the first one is the attractive potential. So the attractive potential is trying to attract the vehicle to the destination. So assume there are no obstacles in the space. So for the attractive potential, we may define this UA similar to the function we used before. So we can define this one to be a half KA with rho A square. So this rho A is the distance. It reflects the distance between the vehicle and your destination. In this way, we define the attractive potential, and this attractive potential is somewhat reflect the distance, linked to the distance between your vehicle and your destination. But I would say that this function is not the only way. It's not unique. It's not the unique way to define the potential. So you may define the potential in another way. But this function is one of the functions that has been popularly used. So from this attractive potential, we can calculate the force. We can calculate the attractive force. So it's attractive force. So in the 2D space, you know the force will be a vector. It will be a vector, so we can represent the vector in the form of FAX in the x direction plus FAY in the y direction. So I just use this form. That is I, this is G. You may use different ways to represent the vector. So the FAX will be equal to minus BUA dx So in this equation, the Ka is just a constant. So the Ka is a constant. Also, it's a design parameter. So typically, the designer need to choose or to tweak this constant. And the Xa and the Ya are the coordinate of your destination. So the function is just in terms of x and y. So you can calculate this one. So you can try this. You can try this by yourself. It's not difficult. So if you do this, you will find this equal to minus Ka x minus Xa. So I will encourage you to do this, to try it by yourself. Fay, similarly, we can define this equal to minus BUA dy. So this equal to minus Ka y minus Ya. So do you have any problem to calculate this one? For this one, you can easily calculate by this UA equal to half Ka x minus Xa square plus y minus Ya square. Then when you calculate the derivative in terms of x, then this one become a constant. So it will become zero. So this BUA dx equal to a half Ka multiplied by 2x minus Xa. So this 2 is cancelled. So it becomes the Ka x minus Xa. So this one of the method is the first method. And a more general method is to use the chain rule. So we have this BUA dx. So now the UA is the function of in terms of UA. So it's this UA in terms of UA in the half Ka rho A square and multiply by B rho A dx. So for this one, it's become half Ka multiplied by this 2 rho A. So multiplied by, so this d rho A dx given by this equation. So this is rho A. So it's more complicated. So this equal to a half multiplied by this one multiplied by this one. So this one is actually just rho A. So this one is just rho A and multiplied by this internal part. So multiplied by 2x minus xa. So this 2 is cancelled. This rho A is cancelled with this one. So this 2 is cancelled. So this gives you Ka x minus xa. So this chain rule is quite general, can be used to solve any complicated equation. So for this simple equation, actually you don't need this method, but for the next equation, for the next potential function, you will find this one is quite useful. So firstly, we define this attractive potential. So the attractive potential is trying to attract vehicle in any location to your destination, but there are no obstacles in the way. Secondly, we need to define for the obstacle. So for the obstacle, we define this repulsive potential. Repulsive potential. So the problem formulation is from the starting point to your destination. So there is an obstacle in between. So we got an obstacle at here. So the repulsive potential is try to solve this kind of problem. So the idea is something. So the idea is something like this. We got your vehicle, your current location, and we have a destination. So the attractive potential is trying to attract your vehicle to your destination. And you got a higher potential if your vehicle is further to your destination. So the potential will decrease when you become closer to your destination. So these are the attractive potential. For the repulsive potential, this repulsive potential only defined within the obstacle. And the center of the obstacle got the highest potential. So the obstacle, the repulsive potential is trying to repulse or to push your vehicle outside this obstacle. So if you enter the obstacle, if you are closer to the center, then the potential becomes larger. So you got a higher force, larger force to push your vehicle outside, out of the obstacle. So this is the physical idea of the method. Then how to define this repulsive potential? So also there are different ways to define this repulsive potential. So to define this repulsive potential, assume we define the center of your obstacle to be X obstacle, Y obstacle. And we define this radius of your obstacle to be rho 0. Rho 0. So we define this repulsive potential to be something like this. So if your vehicle are outside of the obstacle, it will be 0. So if the distance is greater than rho 0, so here we define this rho to be the distance between your obstacle and between your vehicle and the obstacle center. So assume your vehicle is at here, then this distance are defined by rho. So if your vehicle is outside the obstacle, this repulsive potential is not working. So we define this energy to be 0. So if your vehicle is inside the obstacle, so we define a potential function. So the potential function, so there are also many ways to define the potential function, but we try to define the potential function that it becomes larger when you are closer to the destination. So for this purpose, we can define the function in this way. A half kr is also a constant 1 divided by rho minus 1 divided by rho 0. Square. So this gives the vehicle is inside the obstacle. So once we define this repulsive potential, we can define the repulsive force. We can calculate this repulsive force. So the Frx is equal to minus dur dx. So because the ur is defined by two paths, so there will be two paths. So 0 if the rho is greater than rho 0. So if the rho is smaller, is within the obstacle, so you need to calculate this derivative. So I will leave this to you to try it. So try to calculate the derivative of this function. Derivative of this function. So similarly, we can calculate the repulsive force in y direction, so E minus b ur dy. It's also got 0 if the vehicle is outside the obstacle, but not 0 if it's inside the obstacle. So also it's leave to you to try this. So if you check the previous papers, you know this is one of the previous questions. Previous questions ask you to derive the equation for the repulsive force. So it's important that you know how to calculate this. So you can use the chain rule to try to derive the derivative equation. So now we have defined the attractive potential and the repulsive potential. So we are now ready to formulate the problem. So we can get our differential equation. Differential equations. So it's x dot equal to vx, so these are quite standard, and the y dot equal to vy, and the vx dot equal to ax. So we know this equal to fx divided by the mass. So the fx will be the summation of all the forces. So it's including the forces, including the attractive force, the repulsive force. So if you got any additional force, you can put it here. So this divided by m. So the Vy equal to the Ay, so equal to Fy divided by the mass. So similarly, this is equal to Fy, attractive force, plus the repulsive force in the y direction, and plus any other force that you have defined. So these are the differential equation, the set of differential equation. So similarly, you will get your initial condition. Initial condition, for example, your initial time for the t equal to 0, you got your x0 equal to your starting point, x0, and your y0 equal to the y0. So these are the starting point. And you got your initial velocity. For example, this equal to 0, your Vy0 equal to 0. It's a static position. And for the m, typically we can normalize this m to be V1. V1. So for the final condition, you know, for the time of Tf, we have the desired x Tf equal to the destination, and the y Tf equal to the Yp. So these are the destination. So you can define a similar velocity in the final state. For example, with 0, your Vy Tf equal to 0. So from here, you got a set of second order differential equation. So if you solve this differential equation, you will got your x, t, and y in terms of t. So this set of x, y will be coming from your starting point eventually to your destination. You will got a set of paths like this. But generally, it's quite complicated to solve this differential equation by hand. It's very complicated. So typically, we use the computer to help us to do this. So this will be part of the first assignment. So you to use this method to design a path to the real problem. Okay, so that's all for today. So I will put the slide on this spectrum model. So it will be under the same well name. So you can